All right, guys, I'm back with another topic here. So this video covers various techniques of feature engineering. So moving ahead, in our data set, we know that we have categorical columns and as well as numerical columns. So for categorical columns, we can get one-hot encoding features. So for doing that, we need some helper functions to solve the task. So here I have a function that basically separates categorical columns and numerical columns from the data frame that you pass. So this is my parameter or input parameter here, and it should be data frame, okay? And here I'm getting the column names, list of df.columns. After this, I can extract numerical columns by using get numeric data. It's a method that is pandas method basically. So it is only used for data frames. df dot get numeric data dot columns. So this code extracts numerical data frame. From that data frame, we need to extract columns, and we are getting it as a list, basically numerical columns. And to get categorical columns, what we can do is we can simply do set difference. So we can take, we know columns in data frame are unique in the sense column names. We cannot have same column name multiple times. Pandas will automatically uh, does some string manipulation and appends it in the data frame, but that's different case. So to get just get the categorical columns, you can simply do set difference, set of calls minus set of numerical calls, and just get the list form, and then return the separated categorical columns and numerical columns. This function is helpful in so many ways in the coming part. Now I have another function that extracts dummies, basically one-hot encoding vectors. So we have a method in pandas such as get dummies. So in this function, we have two parameters, data frame and column. Call df equals df of call, basically selecting the one column. And we need to return the dummies of that column. Okay, that's very simple. And here I have another function that basically encodes multiple columns into one-hot encoding vectors. So here it's taking two parameters, df, ignore columns, which is given a default value, that is ignore columns, which is this value, this variable. So we don't want to convert these columns into one-hot encoding. This is our target. So we cannot convert, we cannot do any sort of manipulation in for the target variable. And time is a different column because we have date plus hours plus minutes plus set. Yeah, that's what we have. And we don't want to mess up with the time, as well as address. Address is a column that has the exact place where the crime occurred, right? It's different from address type. And then we have date. Date is the year, month, and day format, the type of data we have. So we cannot convert into one-hot encoding. So we just need to ignore those columns. And that's why I'm passing it here. Now what this function will do is, it will get the categorical columns and numerical columns from the data frame that we pass. This is the function I'm using. And then I have this list, multi-feature dummies equals list of df of num columns. This list already holds a data frame in it, which has numerical values, numerical columns and values. So we don't want to mess that up. So I'm just storing this in this list, and then I'm using a for loop for I in categorical columns. If I not in ignore columns, that means this, which is again this. If I not in ignore columns, d equals extract, d is nothing but dummies. D equals extract feature dummies, df equals df, column equals I, which is this function basically. Once we get this, we need to append this value, this variable in this list. So I keep on appending for all the categorical columns that are present in my data frame, except these columns. Now, once I have this list that contains dummy data features and the numerical features, I just need to concatenate them to create a big data frame. So here I am doing the concatenation part. pd.concat multi-feature dummies axis equals 1. This signifies that we are concatenating column base. Return encoded data. That's what this function is doing. This is for categorical featureization, data featureization. Now comes spatial distance features. Remember, in our data, we have coordinate values, latitudes and longitudes. So using those columns, those values, we can extract some distance-based features, which can add value in our whole pipeline. Since we are dealing with the crime data, and we know that usually crimes get reported in the nearest police station, right? So as a creative and programming hack, what I implemented, this I did not find any of the references which I, referred for, but this is something I tried on my own. So what I did is take different police stations available in San Francisco City. These are the different police stations that are available in the whole city. And apart from this, apart from police stations, I'm also taking tourist places, like we have a wine country, Golden Gate, National Park, etc. This is I didn't try initially. I didn't consider this, but still I considered it. It's good to have more features, and we can again select best features out of it. So I have taken these many coordinate values in a dictionary. You can see this dictionary. And once I have this, I can calculate Haversine distance between each coordinate in the whole data set with each value in this dictionary. That's what this function is all about. Get distance ij, I equals ij of 0, first place, j equals ij of 1, second place, second coordinates. I mean, second set of coordinates. Like imagine this as a list having two coordinates of two places. Like first value is the coordinates of one place one. Second value is the coordinates of second place. Distance equals Haversine distance, origin equals I, destination equals j. This Haversine distance is a function available in NPU package. Remember, we installed that initially. So once we have this helper function, we can now extract the distance based features for all the columns and all the values with respect to each key here. So this function has these many parameters: data frame, latitude column, longitude column, place names, and place coordinates. So I'm just taking the values in a list here first. Df of lat column dot to list. It considers the latitude column in the form of a list, big list. Similarly, lon values. Then what I'm doing is I'm converting, like I'm simply taking the zip format of these two. Okay. And then what I'm doing is I'm again converting this with respect to this in the form of a zip. Okay. And after all this, I'm using this function to calculate distance between each data value of latitudes and longitudes with respect to each key here. That means this. So this is a magic function, magic code, one-line coder. Without using for loops, we can implement with simple maps and lists, so we can do it easily. And once I have this, I can append the distances in this data frame. So p name is my place name. That means each key. So that's about this function. So once this is over, we can now compute get the spatial distance features in this code. Like again, concatenating and using the above functions. So as you can see, I'm having a list here, empty list for p name, comma p coordinates in stations.items. So stations is nothing but my parameter here, which has a default value that is this. And I'm getting the latitudes and longitudes. I'm passing those column names in this function. I'm getting the features. I'm appending this value variable in this list. And finally, concatenating them into a big spatial distance features data frame. Return spatial distances. So we can execute this code here. So this output that you see here is nothing but the print statement, which is getting executed. Okay. So this is about the spatial distances. Coming to internal workings of this function, since you are dealing with coordinate values, to find the distance between two coordinates, we cannot use Euclidean distance. We cannot use that technique because of some concepts like CRS, that is a coordinate reference system. We will be calculating the distance in a 2D, but we know that Earth is 3D, and we can't change that. And there is some mathematical proof with which this function implements, and with the help of that function, uh, the distance that we get is quite similar, and we can easily use it for both 3D and 2D. That's a different topic and different concept. But just as of now, imagine we are just calculating the distance between two coordinates. That's it. So once after getting this, what the next step is that doing some arithmetical operations on coordinate values that we have. The simple addition, subtraction, squaring, multiplication. So these are referred in Kaggle discussions. and they found out that this helped them improve the score. This technique basically, uh, mathematical operations, and I thought, why not I implement that? So yeah, it's a good place to learn from the like-minded people here, and that's really good. So here it's just doing sum. So we get to see the code here, and similarly difference, subtraction basically, and then summing it up and then squaring it. And after that, subtracting and squaring, and square, latitude square plus longitude square, and then take the square root of that. Simple arithmetical operation. They found out it happens to be working for them. So it's just another way of feature engineering. Ln square minus lat square whole square root. So these functions are helper functions with which we can map it one line coders and get the values for each for each column and row. So this is how we get like simple one line coders I'm using after taking the coordinate values and returning that as well. So we discussed in this video three ways of feature engineering. One is one-hot encoding. The other one is distance-based features, and the last one is nothing but arithmetical operations computed on coordinate values. Simple stuff. Please go through this and try to debug it when you are implementing. That's it for this video. In the coming video, we'll discuss how we can featureize the address column. Until then, goodbye.